And really their popularity and their success, I think, was based on who had the biggest beard. Back thousands of years to when scientists looked like this. And really their popularity and their success, I think, was based on who had the biggest beard and the whitest toga. And this guy had the biggest beard and the whitest toga of them all, at least when it came to matter and the atom, because he was the one, Democritus, that coined the term atomos. And what he theorized, because really science was just based on theory at that point, what he theorized was that all matter was made up of these tiny, indivisible particles, and that these particles were all different, and they retained the properties of the substance that they were meant to describe or be a part of. So things like oil would be really slippery spheres that could slide over one another. Prior to this, things were thought to be made up of the 4 elements, and just varying compositions of those. So if we take the term atomos and the idea that we can have these indivisible particles, and we move ahead several thousand years to a fellow by the name of John Dalton, we start to get a better understanding, or a more current understanding, of our model of the atom. And what he came up with was very similar to what Democritus proposed, which was that atoms are tiny indivisible particles, but he did so based on science, observation, experimentation. And what he found was that atoms, when they combined, did so in definite proportions. So that when things combined, they always did so in the same ratio. And he hypothesized that these tiny indivisible spheres, which he envisioned look a little bit like this, were the same for all substances that were the same, and were different for different substances. So for example, he theorized that gold atoms would all be the same as other gold atoms, but they'd be different than copper atoms, but all of the copper atoms would be the same as other copper atoms. So he came up with several tenets of his atomic theory that held for many numbers of years. Now, as we continue to fast forward, we can see that Dalton was just the beginning of evidence-based science. That as more and more scientists were starting to evolve their theories based on experimentation and not just observation. And what he came up with sort of cracked open Dalton's idea of what an atom was. That is, maybe atoms aren't indivisible. Maybe they are made up of smaller particles. And his experimentation with cathode rays and their response to magnetic field helped him to theorize that perhaps there are these tiny negatively charged particles within the atom. And that these tiny negatively charged particles, which further became known as electrons, were interspersed amongst a positive matrix that allowed the atom itself to remain neutral, but also allowed the atom to respond to a field illustrating that indeed there is a negative charge within the atom. And this became known as the Raisin-Bunn model. And if we take a look at this depiction of the Raisin-Bunn model, we can see that these negative charges appear to be fixed, although Thomson, to his own admission, thought that they started to spin around or move around this particular version of his atom. It's important to note that while Thomson theorized that there must be some positively charged particle in the atom to offset the negative charges, he never conclusively proved that they were there. That took an individual by the name of Ernest Rutherford and his famous gold foil experiment, or Geiger-Marsden experiment. And you might recognize the Geiger name from Geiger counter fame. But what they discovered was that these atoms do in fact contain positively charged particles. Now, how did they do that? Well, like many things in science, the discovery of these positively charged particles within the atom came about pretty much by accident. Rutherford had directed Geiger and Marsden to perform a series of experiments that would confirm some of his ideas about how radioactive matter behaved. And what he had them set up was what became known as the gold foil experiment. That is, he had a piece of radioactive material that was emitting these positive alpha particles that should be transmitted through a piece of thin gold foil, hence the name. Now, what Rutherford thought was that these alpha particles would all pass completely through the gold foil. Remember, atoms at the time were thought to be neutral, that they had the negatively charged particles within that positive gooey matrix of the Raisin-Bunn model. But what was found was that some of these alpha particles, these positively charged particles, were being deflected as they moved through the gold foil, and that some of them, in fact, were being reflected back. Now, what the evidence led to was Rutherford's hypothesis that atoms are made up of mostly empty space, and that there's a tiny, intensely positive nucleus or core that contained these positively charged particles. And so Rutherford's model is Rutherford's hypothesis that atoms are made up of mostly empty space, and that there's a tiny, intensely positive nucleus or core that contained these positively charged particles. And so Rutherford's model looked a little bit more like this. Now the atom's starting to look a little bit more like we tend to think of the atom now, isn't it? But we're not quite there yet. If we believe that these positively charged particles are within the nucleus and that we have these negatively charged particles swirling around the nucleus, it would lead to the idea that these negatively charged particles would be attracted to the positively charged particles and go spiraling into the nucleus. Now, since we're all here, that clearly doesn't happen. So how is it that the electrons don't go spiraling into the nucleus and destroy all matter and life as we know it? Well, we can thank Niels Bohr for getting that ball rolling. Now, Bohr's idea was that electrons could only occupy fixed paths or orbitals around the nucleus. That is, they could only be in one place or another and never in between. And he referred to these energies as being quantized or having specific amounts of energy. Now, you can envision it kind of like a set of stairs. This ball representing an electron can only be on one stair or another, never in between. And in that way, the electrons could maintain their momentum and not go spiraling into the nucleus if they have to be and can only be found in these specific and set energy levels. And in fact, there was evidence for Bohr's model, although it really only applied to one electron systems like a hydrogen atom. Now, the last piece of the puzzle is what's located in the nucleus. You see, if we step back for a second, we can say, well, if the nucleus does contain these positively charged protons, why don't they repel each other? After all, like charges repel. Now, it wasn't until the 1930s that an individual by the name of James Chadwick ultimately came up with evidence that proved that there are these neutralizing particles, or neutrons, within the atom's nucleus itself.
Thanks to CuriosityStream for sponsoring this video. Engineering materials are normally split into 4 categories: metals, polymers, ceramics, and composites. Understanding the different types of materials, their properties, and how to use them effectively is a crucial part of engineering. In this video, we'll explore metals, their microstructure, and different techniques like alloying and heat treatment that can be used to improve their properties. Around 2/3 of the elements in the periodic table are metals, although for engineering purposes, we're particularly interested in just a handful of them. Iron is probably the most important of them all, because it's used to create steel, a high-strength material with a wide range of engineering applications. Aluminum is commonly used because its alloys have high strength-to-weight ratios. It has a relatively low melting temperature, which makes it easier to process and use for casting, and it's relatively inexpensive. Like aluminum, titanium has excellent strength-to-weight properties, although it is even stronger, making it a popular choice for aerospace applications. Its high melting point makes it suitable for applications at high temperatures, but makes processing more difficult. It's also much more expensive than aluminum. Other important metals include magnesium, copper, and nickel. The key to using these metals effectively lies in understanding how they're structured at the atomic level. The atoms of a pure metal are packed together closely and are arranged in a very regular grid. Because of this regular structure, metal is what we call a crystalline material, and the grid the atoms are arranged in is called the crystal lattice. Not all materials have a regular structure like this. In glass, for example, the atoms are arranged randomly, so it's an amorphous material, not a crystalline one. We can think of the crystal lattice as a repeating number of identical units that we call the unit cell. There are several different ways the atoms of a metal can pack together, which means that there are several different types of unit cell. At room temperature, copper atoms, for example, pack together as shown here, where there is an atom at the corner of each unit cell and one at the center of each face. We can see this better if we shrink the size of the atoms and display the bonds between them. This is called the face-centered cubic structure, or FCC. But iron atoms prefer to pack together in a structure where the atoms at the center of each face are replaced by a single atom in the middle of the unit cell. This is the body-centered cubic structure, or BCC. And titanium atoms prefer to pack together in what's called the hexagonal close-packed structure. These are the three most common crystal structures in metals. Both the FCC and the HCP structures have a packing factor of 74%, meaning that the atoms occupy 74% of the total volume of the unit cell. The BCC structure is slightly less closely packed, with a packing factor of 68%. The close packing of the atoms is one of the reasons metals have much higher densities than most of these structures. Both the hexagon placed by a single atom in the middle of the unit cell. This is the body-centered cubic structure, or BCC. And titanium atoms prefer to pack together in what's called the hexagonal close-packed structure. These are the three most common crystal structures in metals. Both the FCC and the HCP structures have a packing factor of 74%, meaning that the atoms occupy 74% of the total volume of the unit cell. The BCC structure is slightly less closely packed, with a packing factor of 68%. The close packing of the atoms is one of the reasons metals have much higher densities than most other materials. In reality, lattices aren't perfect like the one shown here, but contain numerous defects, of which there are several different types. A vacancy defect occurs when an atom is missing from the lattice. An interstitial defect occurs when an atom squeezes into the gap between existing atoms in the lattice. This is a self-interstitial defect, since the extra atom is of the same element as the lattice, but interstitial defects can also be created by impurity atoms of a different element. And then we have substitutional defects, where certain atoms in the lattice are completely replaced by impurity atoms. These are all point defects, because they affect a single location within the lattice. Lattices also contain linear defects, called dislocations, where a number of atoms are offset from their usual position in the lattice. The first type of dislocation is an edge dislocation, where the lattice contains an extra half plane of atoms. Let's shrink the atom size so that we can show the atomic bonds. This is a stable configuration, but when a stress is applied to the lattice, the atomic bonds break and reform, allowing the extra half plane of atoms to glide through the lattice. Another type of dislocation is the screw dislocation, where an entire block of atoms is shifted out of alignment with the perfect lattice structure. It gets its name because if you follow a path of atoms around the dislocation, it will spiral down through the lattice like the thread of a screw. Again, when a shear stress is applied, the atoms rearrange into a new stable configuration. Most real dislocations will actually be a combination of edge and screw dislocations. Because dislocations move through the lattice by the breaking and reforming of atomic bonds, the process is irreversible. A dislocation doesn't return to its original position when the applied shear stress is removed. This is the underlying mechanism behind plastic deformation in metals. It's essentially the motion of a large number of dislocations at the atomic level. Elastic deformation is caused by the stretching of atomic bonds. Unlike the motion of dislocations, this stretching is completely reversed when the load is removed. This graph shows how a material's yield strength changes with dislocation density. Materials that contain a large number of dislocations have improved strength, because dislocations can get tangled, preventing each other from moving through the lattice. The motion of dislocations through the lattice is also affected by how the atoms pack together. It's easiest for dislocations to move along planes where the atoms are closest to each other, since it's easier for those bonds to break and reform. This corresponds to different planes depending on the structure of the unit cell. In reality, even pure metals don't maintain a regular crystalline structure over long distances. Let's zoom in to some molten metal and see how it solidifies. As the metal cools down, atoms group together and a lattice structure begins to form in several different locations at the same time. Each of these lattices has its own orientation, and as the metal cools down, the lattices continue to grow until it has completely solidified. We end up not with one continuous lattice, but with multiple lattices that are oriented in different directions. This creates what we call grains within the metal structure, and materials made up of a collection of these grains are said to be polycrystalline. The grains are separated by grain boundaries. Since each grain has specific planes along which it's easier for slip to occur, the presence of grains impedes the motion of dislocations, and so polycrystalline materials tend to be stronger than materials made up of a single uniform crystal. The smaller the grain size, the stronger the material will be. This is captured in the Hall-Petch equation. We can use this information to intentionally strengthen metals by controlling the size of the grains that form as the metal is cooled. Impurities called inoculants can intentionally be added to the molten metal so that crystal nucleation occurs at more sites than it otherwise would have, leading to smaller grain sizes. Another way we can do this is by controlling how fast the metal is cooled. If a metal is cooled very rapidly, nucleation occurs at more locations and the crystals don't have much time to grow, so the metal will end up with a finer grain structure and will be stronger as a result. Controlling grain size to strengthen a metal is called grain boundary strengthening. This is just one of many strengthening techniques. We can also strengthen a metal by plastically deforming it, using techniques like cold rolling or forging. This increases the number of dislocations, and so increases the strength of the material at the cost of reducing its ductility. This is called work hardening. One very useful quality of metals is that they can be mixed with small quantities of other metallic and non-metallic elements to improve the properties of the base metal in some way. Metals that are created by combining different elements in this way are what we call alloys. We typically split metals and their alloys into ferrous and non-ferrous categories, depending on whether or not the base metal of the alloy is iron. Brass, for example, is a non-ferrous alloy of copper and zinc. It typically contains 65% copper and 35% zinc, although other alloying elements are sometimes added. It is used for its attractive appearance and the ease with which it can be machined. Aluminum alloys are important in engineering and are often used for the good strength properties they provide at a light weight and reasonable cost. Common alloying elements are copper, manganese, silicon, zinc, and magnesium. Aluminum alloys are classified according to whether they're designed to be used for casting or to be worked, and are designated using specific numbering systems. But steel is probably the most important engineering alloy of all. Pure iron is too soft for it to be used for structural purposes, but it can be combined with small amounts of carbon, and in some cases, other elements, to produce steels that have incredibly useful properties. Steels are separated into a few different categories, depending on the amount of carbon and other alloying elements. Low carbon, or mild steel, contains up to 0.25% carbon. It doesn't have particularly high strength, but is ductile and relatively low cost. Medium carbon steel contains between 0.25 and 0.6% carbon, and high carbon steel contains between 0.6% and 2% carbon. Since these steels contain a larger amount of
Welcome to the first episode of Kitchen Matters, a series put together by graduate students at the MIT Materials Science